The first section of C1 is looking at indices, that is to say something written like this. We have a to the power of b. Now this is basically a shorthand for saying we want to multiply a by itself b times. So this is the same as saying we have a times a times a times dot 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 times a grand total of b times. And by using this definition, we're able to create a bunch of derivations for rules which you really should be aware of and are incredibly useful for the entirety of C1. The first rule is to do with what happens if we multiply two indices together. So if we have something like this, a to the power of b multiplied by a to the power of c. So a to the power of b, as we said before, is a multiplied by itself b times. So that's a times a times a times dot 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 times a. And a to the power of c is similarly a times itself c times. So we have b lots of a here, and c lots of a here. So in total, we're able to see that we have b lots of a multiplied together times c lots of a multiplied together. In total, we have b plus c lots of a all multiplied together. And the shorthand for writing that would simply be a to the power of b plus c, because that's the number of a's we have multiplied together. So this is the rule we need to learn. It's that a to the power of b times a to the power of c equals a to the power of b plus c. Of course, we need to note that this only works when we have the same base. So we couldn't multiply 3 to the power of 4 times 5 to the power of 7 and just add up the powers, because we need to make sure that the numbers we have raised are the same. The next rule we have to learn concerns what happens if we're dividing powers. So if we had a to the power of b over a to the power of c, then the numerator of this is just going to be b lots of a multiplied together. So again, a times a times dot 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 times a total of b times. And the denominator is going to be c lots of a multiplied together. So again, a times times dot 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 times a c times. And if we have a fraction like this, everything's multiplied together, so we can just start cancelling. We start cancelling off a's, and for every a we get rid of on the denominator, we have to get rid of a corresponding number of a's in the numerator. So we get left up with b minus c lots of a's multiplied together. And of course, b minus c lots of a's multiplied together is equal to a to the power of b minus c. So we can see that when we have the powers multiplied together, then we just add the indices. And when we have one divided by the other, we just subtract the indices. And they're your two basic rules of indices. The next rule of indices which we need to consider is what happens if we have a power raised to another power. So for example, if we have something of this form, with a to the power of b, all raised to the power of c. So we need to look at what this actually means. This means that we have a to the power of b times a to the power of b times a to the power of b times dot 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 times a to the power of b, and all of that happens c times. And if we look at our first rule of indices, which is up here, a to the power of b times a to the power of c equals a to the power of b plus c. So, if we had a to the power of b times a to the power of b, then that would be a to the power of b plus b, which is a to the power of 2b. If we have 3 of these multiplied together, it'd be a to the power of 3b. 4 of them, a to the power of 4b. So you can see that if we have c of them multiplied together, our final result is a to the power of bc. And that's our rule for this indice. If we have something to the power of something in a bracket raised to the power of something else, you simply multiply those two powers together. So this is equal to a to the power of bc. And that's the third rule of indices which you'll need to learn for your exams. The fourth rule of indices which we need to learn is the special case of what happens if we raise something to the power of 0. So, if we have a to the power of 0, what does that actually mean? At first glance, you would think that perhaps that is just 0, but it's a very common pitfall, and we need to remember that it's not, in fact, 0. If we have a look at rule 2, we can see that a to the power of b minus c equals a to the power of b over a to the power of c. And we could rewrite a to the power of 0 as a to the power of 1 minus 1, because 1 minus 1 is 0. So if that's a to the power of 1 minus 1, then under rule b, this is equal to a to the power of 1 over a to the power of 1. And we know that a to the power of 1 is just a, so we can just rub out these little indices. We don't need them anymore. And a divided by a, well, any number divided by itself is 1. So as a result, we can see that a to the power of 0 must be equal to 1, and indeed it is. And that's a result that you need to remember, and you don't want to fall into the pitfall of thinking it's 0. Our next rule considers what happens if we have a negative power. For example, if we have a to the power of minus b. Now it's important to note at this point that a to the power of minus b is equal to a to the power of 0 minus b. A to the power of 0 minus b. And we know that anything to the power of something subtract something, according to rule 2, is just a fraction as such. So this is equal to a to the power of 0 over a to the power of b. However, according to the fourth rule, which we just showed, a to the power of 0 is equal to 1. So therefore, this is equal to 1 over a to the b. So we've shown that if we have anything raised to a negative power, it's the same as 1 over that something just raised to the positive power. A to the power of minus b equals 1 over a to the b. The next indice law that we need to look at is quite difficult to think about conceptually. We're going to look at what happens if we raise something to a fractional power. Specifically, we're going to see what happens if we have a to the power of 1 over b. Now, I'm going to keep in black what we want to evaluate, and we're going to manipulate it, and I'm going to do that in red just so it's clear what we're doing. So we're going to look at what happens if we raise all of this to the power of b. So, put brackets around it, raise it to the power of b. Then, according to our rule here, that a to the power of b all to the power of c equals a to the power of bc, we can see that this is equal to a to the power of 1 over b times b, and 1 over b times b is just equal to 1, so this is equal to a to the power of 1, which is just a. So we can see that what we wanted to evaluate, that is a to the power of 1 over b, all to the power of b, is equal to a. Then if we take the b roots of both sides, we end up getting that what we wanted to look at, that is a to the power of 1 over b, is equal to the bth root of a. So this is what happens when we have fractional powers, and you could show that if we raised all of this to some arbitrary c, then we just put all of this to the power of c. And due to the way that square roots work and other surds, we could put the c inside there. But we're going to show that in just a little bit. But this is the rule we need to learn. A to the power of 1 over b is equal to the bth root of a. So, if we're going to look at a to the power of b over c, that is to say this, then according to our third rule, we're able to split this up into a to the power of 1 over c, all to the power of b. However, when we multiply things together, it doesn't matter which order we do them in. So in fact, we could also have written this as a to the power of b all to the power of 1 over c. And using each of these gets us two different forms which are both equally valid of writing our answer in, and which one you use depends on the numbers in question. It may turn out that the root of a number is a nice number. So, if we take this version, then we know that a to the power of 1 over c, according to the rule that we just showed, is equal to the cth root of a, and then if we raise all that to the b, we simply get cth root of a all to the power of b. Whereas if we use this version, we can show that this is equal to, we get a to the power of b and the cth root of all of that. So this is simply equal to the cth root of a to the power of b. So we've shown that it doesn't really matter where this indice, this ultimate indice on the top of our original fraction lies, whether it's inside the root or outside the root, it actually is exactly the same thing. It's important to note this because it may make your life very easy when you need to simplify certain indices. So these are the 7 rules of indices which you'll need to learn in order to deal with a question on indices or simplification of expressions in general. If we have two indices multiplied together and they have the same base, then you simply add the powers up. So a to the power of b times a to the power of c is equal to a to the power of b plus c. If we have one divided by the other, we simply subtract the indices. So a to the power of b over a to the power of c is equal to a to the power of b minus c. If we have one raised to the power of the other, we simply multiply the indices together. If we have something to the power of 0, no matter what that something is, then that's always equal to 1, which is a very useful result. If we have something to a negative power, then that's the same as 1 over something to that positive power. So a to the minus b equals 1 over a to the b. If we have something to a fractional power, then the denominator of that fraction simply becomes the degree of the root that we put that number to. So a to the power of 1 over b is simply the bth root of a. And similarly, if we have it with a fraction where 1 is not the numerator, then we just raise our result to the power of that numerator. And as we showed earlier, it doesn't matter whether it's inside or outside that square root sign. So now we're going to have a look at a few example questions where these rules are useful, so you can see how they're applied. So the first question we're going to look at is how would we simplify a to the power of 3 all to the power of 3, or a cubed cubed. Now, as we can see, we have a power raised to another power, so we're going to use our third rule, that is to say a to the power of b all to the power of c equals a to the power of bc. So all we have to do is multiply these two indices together. In this case, 3 times 3 is equal to 9, so this is simply equal to a to the power of 9, and that will be our answer. The next question we're going to look at is 2x cubed multiplied by 5xy. It's important to remember that whenever we have letters next to each other, or numbers in front of letters, then that implies that we're just multiplying them all together. So in reality, we have here 2 times x cubed times 5 times x times y. But in maths, it doesn't matter if things are all multiplied together, that is, which order we do these operations. So we can just as easily say this is equal to 2 times 5, which is 10, times x cubed times x, but according to our first rule, we can see that x cubed, where a is now x, and our cubed, our 3, is b, multiplied by x, where x is the same as x to the power of 1, x cubed times x is equal to x to the power of 3 plus 1, that is to say, x to the power of 4. So this is equal to 10 times x to the power of 4, and we only have one y, so we just multiply by that y. So our final answer is that 2x cubed times 5xy equals 10 x to the power of 4 y. This is an example of a slightly harder question, where we have 12x to the power of 4 y squared z divided by 4x cubed y squared. It's important to remember that division can just be represented by a fraction, so this is equal to 12x to the power of 4 y squared z, all divided by 4 x cubed y squared. And I've left the gaps in between them because, as the letters are just next to each other, these are all multiplied together. So if we simplify this, we can see that 12 over 4, 12 divided by 4 is just 3. Then we have x to the power of 4 divided by x cubed. Using our rule here, we can see that is just equal to x. And then here we have x squared divided by y squared divided by y squared. And anything divided by itself is 1, so that's just times 1. If we multiply by 1, it doesn't make any difference, so we can ignore it. And then we have z divided by 1, so that just stays as z. So our final answer is 3xz. The final idea which we need to learn is that if we have a to the power of b is equal to a to the power of c, and that a is not equal to 0 or 1, because if a were equal to 0, then 0 times itself any number of times is still 0, and similarly, if it's 1, 1 times itself any number of times is still 1, then if we know this to be true, then this implies that b is equal to c. For example, if I have 2 to the power of 4 equals 2 to the power of 4, then 4 equals 4. To give it numbers, simplest way of looking at it. So if we were given the question where we had 2 to the power of x equals 16, we know that 16 is equal to 2 to the power of 4. So we can equate what we have in the powers. We're able to see that x equals 4. And we're able to use this idea to help us deal with more complicated questions. So, if we have a question like this, 3 to the power of 2x minus 1 equals 27, our first challenge is to rewrite 27 in the terms of 3 to the power of something. In this case, because it's quite a low number, we can see and show quite trivially that 27 is equal to 3 cubed. So that's equal to 3 to the power of 3. Now, because both of these have the same base, we can say that the powers that they're raised to, because we know they're equal, the powers they're raised to must also be equal. So we know that 2x minus 1 is equal to 3. And now all we have to do is add 1 to both sides to give us 2x equals 4. Therefore, x must equal 2. And then we can sub this into our original equation to see if it's correct. So 3 to the power of 2 times 2 is 4, minus 1 is 3, so 3 to the power of 3 does indeed equal 27. So we know we found the correct answer. So that's all you really need to know about the laws of indices for C1. However, you'll find that they're useful not just in questions explicitly about indices, but also throughout the whole of your mathematical career. Indices really are very, very useful, and knowing how to simplify and cancel them down makes your life a lot easier, because you don't want to be having to put really complicated expressions into a calculator. If you're able to simplify it on paper, it saves you time, and makes it far less likely that you're going to make a silly mistake. So, commit these to memory, because you could derive them in an exam theoretically, but it'd be a waste of time. And if you learn them, you're able to rattle them off really quickly, and at the start of the paper, there's some great easy marks for you to get. Thank you for watching. I hope you found it informative and enjoyable. If you have any questions or comments about the video, feel free to post them below. There should be a comment section. And if you have any particular questions which are causing you trouble, you're just not able to simplify them or work out an answer, email them to me, questions@mathematicalsupport.net, and I'll try and provide them as worked examples as video responses.